So we begin with another new chapter, and this is differential equation, the last chapter of your calculus. And in this class, we are going to complete the whole chapter. So it is going to be a hurricane class, but I hope you will be able to understand because the whole chapter is pretty much based on integration only. So if your integration is good, then definitely you don't need much to understand here in this chapter. So it's just that the techniques, and finally at the end of the day you have to do an integration. So let us begin. Now we are going to discuss three things, that is how a differential equation is formed. Then we are going to talk about the order and degree of a differential equation, and then finally we are going to talk about the solution or the different methods of solution of a differential equation. Now let us come to the first part, formation of a differential equation. So how a differential equation came into existence, or why we need a differential equation. Now to begin with it, let us understand what we mean by a family of curves. Family of curves mean it is a set of curves which follow a similar property. Now similar property means, in the sense, the similar property can be slope of the tangent, the curvature of the curve. These are called family of curves. So if we take one example, say for example, if we take this, x square plus y square equals to r square. Now this is representing a family of curve where all the circles are centered at origin and with a radius r. So the r, if we change the r, we get different circles. But what is the common property of all these circles? The common property being that all these circles have a center at origin. Then let us take another example, y equals to mx. Now y equals to mx is representing all those straight lines which are passing through the origin. So if we change m, we are going to get the different straight lines, but all these straight lines have a common property, and that common property is that it is passing through the origin. So therefore y equals to mx is representing that whole family of curve or whole family of straight lines which are passing through the origin. Right? Next, so we can see that in a family of curve, the most important factor is the arbitrary constant. So in the first case, x square plus y square equals to r square, that r was the arbitrary constant. In case of y equals to mx, that m was the arbitrary constant. So if I go on changing the value of r, I get different members of the family. So for example, if I have, say, x square plus y square equals to 4, or that is 2 square, so it is giving me a circle which has a center at origin but with a radius 2. Now if I say x square plus y square equals to 1, so it is giving me another circle with center at origin but the radius is 1. So as I go on changing the value of r, I am going to get the different members of the family. Now here comes a point, here comes a problem, that this r is arbitrary constant. So to get the different members of the family, I have to go on changing the value of r to get the different members. So now if I want to represent all the members by a unique equation or by a unique formula which is going to be devoid of the arbitrary constant. Devoid of the arbitrary constant means there should not be any arbitrary constant. The formula should be unique for all the members of the family. So that one particular equation or one particular formula is going to represent all the members of the family of that curve. Then To do so, so take one example. Say for example, I am taking this very one, x square plus y square equals to r square. If I do a derivative, that is 2x, if I do this derivative, 2x plus 2y dy dx equals to 0, or if we just remove the 2, then y into dy by dx plus x equals to 0. Now you can see this is one equation that we got, which is basically derived from this family of curve x square plus y square equals to r square, but this equation does not have an arbitrary constant, and you are going to get the same equation, doesn't matter whatever the value of r is, because it is a constant, the derivative will be always 0. So this equation is representing the whole family of circle with center at origin. So irrespective of what the radius is, so it really doesn't matter what the radius is, but it is representing all the circles with center at origin. So therefore, this particular equation, as it contains x, y, and the derivatives, different derivatives, or particularly here we have the first order derivative, that is why it is called a differential equation. Differential equation means an equation containing a differential. So here the differential being a derivative, right? So this is exactly what I said. Now, before we move on to the order and degree, so let us solve a few problems where we are going to see how the differential equations are formed for different families of curves. So I'm back to school. So let me take a few problems and let me solve. So we are starting off with formation of differential equation. First problem. The question is, form a DE representing the family of curves. Representing the family of curves. Question number 1. X by a plus y by b is equals to 1. So remember, whenever we have two or more parameters or two or more arbitrary constants, then I have to do the derivative twice. As many number of arbitrary constants, that many derivatives there should be. So as I have two, I must do twice. So therefore, after first derivative, so this is our differential equation for this family of curve. Let us take second example. Example number 2. Same situation, I have two arbitrary constants, so let me do the derivative. So dy by dx, that is equals to 2 e to the power 2x a plus bx plus into b. Now This is basically your y. So this is 2y plus b, or I have left it out this constant y because after another derivative this constant will become 0. So let us do the derivative once again. So e to the power minus 2x, if I take common, so let me take common. So now if I do the derivative, this is minus 2 e to the power minus 2x dy by dx minus 2y plus e to the power minus 2x. This becomes e2y by dx2 minus 2 dy by dx is equals to 0. So now let me just write everything once again, taking this e to the power minus 2x on the other side. So I am left with minus 2 dy by dx from here, and then this minus 2 dy by dx. Okay, let me write it. Right? So this is your answer. Next, number 3. Now instead of the equation of the curve, if you are given the just in sentence whatever the curve is given, that is family of circle touching y-axis at origin, then touching y-axis at origin. So therefore this is how the circle will look like, touching y-axis at origin. So the center will be on the x-axis because y-axis and x-axis are perpendicular, we know. Tangent and the radius, they are perpendicular. So therefore if the circle touches y-axis at origin, then this is the radius r and this is the point. r comma 0. So therefore equation of this circle will become equals to r square. So now I need to find the differential equation of this. So this is the equation of this circle. So now let me just simplify this out. So this is x square minus 2xr plus r square plus y square. So if we do the derivative, so now let me put this back here. So this is your required equation. Okay, now we come back. So now let us understand what we mean by order and degree of a differential equation. Order of a differential equation is basically the highest order of the derivative present in the differential equation. Fine. So we are going to have the highest order, means it can be dy by dx, it can be d2y by dx2, it can be d3y by dx3, whatever is the highest order of the derivative which we are having in the differential equation, that is called the order of the differential equation. Next, degree of a differential equation. Now if your differential equation, now degree is a very particular thing, it is not an universal thing. Order of a differential equation is an universal thing for any differential equation, but degree of a differential equation is not a universal thing. So if your differential equation, specifically it is a polynomial of the derivatives. Polynomial of the derivatives means the derivatives are present in the algebraic form with their powers. So like it can be dy by dx, it can be dy by dx whole square, or you have d2y by dx2 or its whole square, whole cube, doesn't matter what. But if it is present in the polynomial form, in that case the highest power of the highest order derivative present in the differential equation is called the degree of the differential equation. And if the differential equation is not in the polynomial form, then you cannot define the degree of the differential equation. Fine. Let us take few examples. First one, dy by dx plus sin y equals to 0. Now this is a first order differential equation. Why? Because the highest order present here is dy by dx, that is the first order, and also you can see you only have the term dy by dx. So you can say that this is a polynomial of dy by dx. So better to say dy by dx with power only 1. So therefore the degree of the differential equation is 1. So let me just write it. Let me first show you all the examples and then let me write it. So these are the 4 examples that I have taken. Now let me write it. So in the first case, the order is equals to 1, the degree is equals to 1. In the second case, I can see the order of the differential equation here is also 1, but here the degree is 2. Why? Because we have a dy by dx whole square term, right? In the third case, order is obviously 2 because this is the second order derivative term we have, and here the degree is 1. Why? Because this second order derivative, this is the highest order derivative and its power is 1, so therefore its degree is 1. This one here, order is 2 for sure because d2y by dx2 is present. Now what is the degree? As you can see, there is a term here, log of dy by dx. So a derivative is inside a log function. Now this is not admissible in case of a polynomial. So therefore this differential equation does not have a degree, or you can say the degree is undefined, right? So these are how the order and degree of a differential equation is identified. Fine. Now let us move. Now solution of a differential equation. For our case, we are going to talk about only first order and first degree differential equations. We are not going to go beyond that. Now let us first understand what does solution of a differential equation mean. Now the solution of a differential equation is obviously, just remember how the differential equation was formed. You were given a family of curve, you did some derivative on it, and you arrived to an equation where you have only the variables x and y and the derivatives, that is dy by dx, d2y by dx2 and so on. So the very family of curve from where you started and you found that differential equation, so if you just reverse the process, then the family of curve can be called as the solution of the differential equation, or rather to say the general solution of the differential equation. So if I want to give you an example, if I had this differential equation y dy by dx plus x equals to 0, then x square plus y square equals to r square is the general solution, because this is the family of curve from where we started off and we found out this equation. So x square plus y square equals to r square is the general solution of the differential equation. Now there is another kind of solution which is called the particular solution. Particular solution means it is not going to give you the whole family of curve, but one member of the family of curve, any one member of the family of curve. So in that case it is called a particular solution. So again, if we take an example, so if I continue with the same differential equation, that is y dy by dx plus x equals to 0, then let us take, for example, x square plus y square equals to 4. Then this is a particular solution of the differential equation. Why particular? Because you can see here this 4 is actually giving you, this whole equation is giving you only one single member of the family of curve, but not the whole family of curve. So therefore that is why it is called particular solution. So if instead I would have had x square plus y square equals to 1 or x square plus y square equals to 9, this would have given me all different particular solutions of a differential equation. So always remember, any differential equation will have only one general solution, because general solution is basically it is giving you that parent family of curve from where the differential equation came, but it can have several particular solution, obviously. Why? Because particular solution is basically it is giving you an individual member of that family of curves, so there can be infinitely many member in that family of curves, so it is just giving you one of them. So therefore any differential equation can have infinitely many particular solutions, but it will have only one general solution. Fine. Now, as we restrict our discussion to first order and first degree, we have three different methods of finding the solution of a differential equation. One is the separation of variables, two is homogeneous equations, homogeneous differential equations, and then linear equations, that is linear differential equations. So we will be taking up each and every single of this and we will be trying to solve few problems. So let us start off with separation of variables. dy by dx is equals to under root 4 minus y square. So this is dx. Fine. So this is your answer. Number 2, let us take this second problem. So from here I can write, I have to separate out the variables. So with dx I need to keep x, with dy I need to keep y. So first y log y dx is equals to x dy. Fine. Or dx by x. Now, if I consider, so this becomes integration. If I consider log y as z, then dy by y becomes dz. So all those things are understood. If it is an easy step, you need not show the step. But if the substitution is little bit complicated, then you can show. So therefore, this becomes log of log y, right, is equals to log x. Now whenever you have log on both sides, it is always good to do what? It is always good to take the constant also in log. So instead of writing c, write log c. Why? Because at the end you will get a nice result. So you get log y is equals to cx. Log x plus log c, it makes it log of cx, and then log is removed. So from here e to the power cx. Fine. Third problem. So e to the power x dy dx. This is tan. If you consider tan y as z, sec square y dy is dz. If you consider e to the power x minus 1 as z, e to the power x dux is dz. So therefore, this is log of tan y or this is your answer. Now we move on to the next one, that is homogeneous equations. So we start off with homogeneous differential equation. Now before we start, we need to know what is a homogeneous differential equation. So let dy by dx is equals to f of x comma y, because the equation may contain x, may contain y. So if I leave dy by dx on one side, then I have f of x comma y on the other side. So therefore, if this f of x comma y is such that f of lambda x, f of lambda y, means lambda is any arbitrary constant. If f of lambda x comma lambda y gives you lambda to the power n into f of x comma y, then I say that f is homogeneous. This n can be, n belongs to the set of integer. It can be positive, it can be negative, whatever, but we will have a particular type. We are not going to have any other types, but n can be positive, negative, anything. So if it is so, in that case it is called as a homogeneous equation. Also, if it is a homogeneous equation, then I can write this f of x comma y as some g of y by x. If it becomes homogeneous, then I will be able to write it as some function of some function g whose variable is y by x. Now, how to solve this type of equation? We consider the substitution y equals to vx. Right? So therefore, dy by dx will become v plus x dv dx. Fine. Now I have to do this substitution in the equation. After doing this substitution, we will see that the variables get separated. And after the separation, we will follow the normal process. So let us take one example. Let us take this example. See, this, so which can be called as f of x comma y. So now f of lambda x comma lambda y, that is lambda square x square plus lambda square y square by lambda square x square plus lambda square xy. So that gives you this, which is same as f of x comma y. So now there is no lambda. So as there is no lambda, I can say there is lambda to the power 0. Right? So therefore, this is a homogeneous equation. So this becomes homogeneous. Check. I have checked the homogeneity. Remember, whenever you are solving homogeneous differential equation, checking the homogeneity is important. You must show this step. This step is important. Now I am doing it for only this problem. For the other problems I am not going to do it, but ensure you do it. Okay. So now let us take y is equals to vx. So therefore v plus x dv dx is equals to right? This is what we get. So this is 1 plus v by 1 minus v this. Fine. Now Now we have to integrate this. So to integrate this, let us do what? Take the negative sign on the other side. So it becomes right. So therefore this is right. So and then you replace v as y by x. So if you do so, your final answer is so keep your answer like this. No problem. Okay. So here I have x by y. So I will take everything in terms of x. So this is 1 plus e to the power x by y. This. So now v plus, so let us take x is equal to vy. X is equals to vy. So if we do so, so v plus y equals to e to the power v minus 1 by 1 plus 1. Right? So If you do this, if you take this as z, then this becomes dz and this is dy by y, so this is log. So therefore, so v is your x by y, so this is x by y plus e to the power x by y is equal to c by y. If you multiply by 1, then it is this. So this is extra criteria given. So for this I have to find a particular solution following this criteria. So we will come to that. Let us first solve it. So right. So x square they get cancelled, and 2 divided by 2, this is v, and this is v square by 2, and v get cancelled. So you have fine. Right? Now x is 1, y is 2. So therefore let me put the values. So if x is 1 and y is 2, so I have minus half equals to log of 1 is 0. So therefore c is minus half. So let me put it back. So therefore the particular solution so now if I manipulate, I get y is equals to this 2 comes up, so this becomes 2x by 1 minus log of x. Right? Clear? Just go through the step once. If you don't understand, I am pretty sure if you just follow the steps, you will be able to understand. I hope the lighting of the room and my voice is understandable to you. Please ensure you just go through the steps. And finally, the third and the last one, linear equations. Any differential equation which is of this form, that is dy by dx plus ey equals to q, where p and q are functions of x only, then this is called a linear differential equation. This is called a linear differential equation or in y. In y. Same happens for x. If I have where p and q fine, then it is called a linear differential equation in x. Fine. Now to solve this, first I need to find something called the integrating factor. So this is integrating factor. Now what is the integrating factor? That is equals to e to the power integration p dx. Fine. So now the final solution will be y into e to the power integration p dx, that is equals to integration q into e to the power integration p dx whole dx. Now this changes for y, I mean the whole thing changes if it is a differential equation, linear differential equation in x. Okay. So let us solve few problems. Let us take the first one. So here P is equals to 2, Q is equals to 6. So integrating factor, that is e to the power p dx, or that is equals to okay. So therefore the final solution y e to the power 2x is equals to integration sin x. Dx. Now e to the power 2x into sin x dx, this is a very known integration, you already know how to solve it, so I am not solving it here because this integration in itself is a huge integration, so please do solve it and write the final answer. Okay? So consider this whole thing as some integration I. Now this is by parts. Consider this as the first function, consider this as the second function, or vice versa, whatever you want, and then follow the integration by parts and solve it. You will get the answer. Fine. Let us take question number 2. Let me write here only. Okay, so see this is dx by dy, that is equals to right. So consider this as z, then this becomes minus dz, so it becomes minus of log z. So therefore this is e to the power minus log of this. This is what it becomes. If you absorb this minus, it becomes 1 by. So therefore it becomes 1 by this. Fine. So therefore x into that, so x by e to the power minus 1 minus 2 is equals to integration q. Q is this, so this is 1 by 2 e to the power minus 1 into this. Now e to the power minus y, if you just take it up there, or if you divide it, then what do I get? This just divide this by e to the power y, then e to the power minus y by 2 minus e to the power minus y. Take the minus common out, then you have this. Now this, if you take this as z, this whole thing is dz with the negative sign. So this is integration dz by z square. So that gives you minus 1 by z. So therefore this is minus 1 by minus 2 plus c. Right? Take it on this side. Right? Now it is told that when x is 0, y is 0. So let us put the value. So when x is 0, y is 0. So therefore 1 by minus 2 that is equals to c. So therefore minus half or multiply, so 2 fine. Or you can write 2x e to the power y plus 1 equals to 0. Anyway, let us move to the last problem. These two gets cancelled. This is your fine. So that's it. Thank you so much. So this was our class. If you have any doubt, please clarify.